Hello and welcome. In this video, we're going to start looking at the area that is formed between the curve of a function and the x-axis. We're also eventually going to talk about what happens if the curve goes below the axis, but we're going to be looking at the area under the curve. So what I want you to do as a warm-up is use what you know about finding the area of a rectangle to approximate the area of the rectangles created in each situation. So I'm going to help you set up the rectangles for B and C, but go ahead and pause the video and find the area of each rectangle in A, where they're already drawn for you, and add them up. And then answer the question that's below part A. Then unpause the video and see how you did. Okay, so for the area here, the area of that first rectangle is 2 is the width, 2 is the height, so it's 4. The area of the second rectangle is 2 by 5, which is 10. The third rectangle, 2 by 3, which is 6. The fourth one, 2 by 1, which is 2. And the fifth one, 2 by 3, which is 6. And if we add all of those together, we can say that if we are approximating, so I'm going to use the approximately symbol, the area under the curve, we're saying that that is about 28 units squared. And there's no right or wrong answer to this second question, which just says, do you think this is an overestimate or an underestimate? It's really just, what do you think? For me, it seems like there's more area that's missing, sort of in this like empty space. It seems like there's more area missing than there is an overestimate. So I would say that I think that this is an underestimate just based on the amount of area that's not being included versus the amount that's sort of like this piece right here is an overestimate here. But it seems overall like this is an underestimate of the area under this curve. Now what you see in parts B and C are the exact same graph, except the rectangles aren't being drawn. So we're going to construct and find the area under the curve, the same curve, but looking at two different ways to do it. So for part B, it says draw rectangles with a width of 2 still that circumscribe the curve. And in case you don't remember what circumscribe means, it means that the curve is trapped under, completely under, using this rectangle. So if I was going to do that here and I have a width of 2, I want this to be completely under, so I'm going to make my rectangle here. So same thing for the next rectangle. I want the rectangle to go up so that the entire curve is below. So why don't you go ahead and draw the rest of the rectangles and then approximate the area under the curve using those rectangles, and again answer the question about whether or not you think this is an over or an underestimate. So if we add the area of all those rectangles together, we get that the area is approximately 40 units squared. And this looks like an overestimate because every single rectangle goes above the actual curve. So we're over counting area, every single rectangle, in fact. Part C asks us to do the same thing, except this time with inscribed rectangles. Inscribed sort of means the opposite of circumscribed. Inscribed means that the curve never goes above the rectangle. So if I was looking at that here, actually my very first rectangle would have a height of 0 because the curve touches at 0, 0, and I can't go up any higher. I can never go above the curve here. So my first rectangle would have an area of 0. If I look at my second rectangle, it's going to go up until it just touches the curve, and that's going to be as high as it gets. So that rectangle would have an area of 8. Go ahead and pause the video and finish drawing your rectangles and finding the area, and then answer the over and underestimate question again. So hopefully you had time to work through that. This looks like a definite underestimate since every single rectangle is under the curve. So we could look at this and say we know that our actual area is somewhere between 18, which is definitely an underestimate, and 40, which is definitely an overestimate. So our drawing in part A actually looks like a pretty decent approximation. It is somewhere between 18 and 40. Now let's look more at why we're having this discussion looking at this area under the curve. So this idea of finding the area under a curve using geometric shapes, which we just did, rectangles, in that past example, is called Riemann sums. And that's really the big idea in this section. In order to do this, what we're doing is we're looking at some closed intervals starting at an a x value and ending at another x value b, and we're breaking that region or that portion of the curve from A to B, we're breaking it up into a bunch of geometric shapes that we can find the area of so that we can approximate the area under the curve. That idea is using Riemann sums. We use different geometric shapes depending on the type of graph, the way a problem is set up to do this, but again, typically when we're using rectangles, this is called identifying or finding the area under the curve using Riemann sums. Depending on the type of problem, we may be told to do this in a variety of ways. We may just be given a curve and asked to approximate the area underneath, and in that sense, you get to use your discretion and decide the best way to go about doing that. We might be told that we need to use rectangles that have the same width, or we need to use a certain number of rectangles, or we need to use trapezoids or triangles. All of those different things could come into play in different ways depending on the problem. But there are a few specific types of Riemann sums that are commonly referred to, so I want to make sure we have that vocabulary down before we move into some examples where we're going to look at the area under the curve. So first up is a left-handed Riemann sum. A left-handed Riemann sum uses rectangles where the left-hand x value of the curve determines the height of each rectangle. So the height is determined by whatever the left-handed value of the x is for that particular portion. Similarly, the right-handed side, instead of using the left endpoints, I'm going to use the right endpoints to determine the height of my rectangle. So left-handed versus right-handed is saying which side of the interval are you using in order to find the height of your rectangle. Midpoint is using, instead of the left-hand side or the right-hand side, it's using the actual midpoint between those two x values to determine what the height of that rectangle is going to be. And then we already referred to inscribed and circumscribed, and we also mentioned that inscribed is always going to be an underestimate. And another name for inscribed is the lower sum. Circumscribed is always going to be an overestimate, and another name for that is the upper sum. So this is just really working through some vocabulary to make sure we understand what's being asked if one of these words shows up in the directions for a problem. So let's go ahead and look at some examples so we can see what kind of problems we're going to be facing. All right, here we go. So for each of these different boxes here, each of these different portions of the example, we're going to be using a different method to approximate the area under the curve. And this little symbol here is something that I use to say that you can use a calculator to save time on this problem or to make your life a little bit easier. But each of these graphs is the same function, f of x equals negative x squared plus 4 from 0 to 2. So where our x's range from 0 to 2. We are going to be creating for each of these 4 rectangles that are all equal in their width, which actually means if we're going from 0 to 2 and we have to break it into 4 pieces, each rectangle for all of these is going to have a width of 1/2. And if you just look down here, each of these is 1/2. That would break it into 4 different rectangles. So let's focus on just drawing the rectangles for each of these first, and then we'll go back through and actually calculate the area. So for a right-handed rectangle, we are going to be looking at the right side of each of these pieces, and that will be determining the height of our rectangle. Then we're going to make our rectangle go from the x-axis up to that height for each of those rectangles. And it shouldn't be going below the x-axis. I'll erase that. And then this last one is actually going to have an area of 0 because the right-handed point is on the x-axis. So again, we went to each spot and we looked at the right-handed value to determine our height. So I'm going to use a different color and try and make those points, the height of those rectangles, a little bit more dramatic so that you can see it. That's creating right-handed rectangles. What we're going to do in this second part is we're going to create left-handed rectangles. So we're going to start at the leftmost part of the curve. In this case, that's when x is equal to 0. That's going to be the height of our first rectangle. We're going to go to the left. That's going to be the height of our second rectangle, the height of our third rectangle, the height of our fourth rectangle, and then we're going to go ahead and draw those. So this first rectangle is going to go all the way up to 4. The second one is going to go up, woohoo, I went too far. It's going to go up to that second height that we identified. The third one's going to go up to that third height, and the fourth one's going to go up to that fourth height. And I'm going to go back and darken those heights for each of those rectangles again. If we were doing this with midpoint rectangles, we'd be looking for exactly halfway between each of these. So halfway between here would be somewhere around here is going to be the height, somewhere around here, somewhere right in the middle. 1, 2, 3, one more right in the middle. And then we can draw our rectangles going up to that height as well. And we'll come back and look at the trapezoid one last. So now how do we find the area of each of these rectangles? Well, the first thing that I want to do is look at, and I'm actually going to use some space down here as scratch. I want to look at the different values of the function that we care about. So we care about what happens when the function is 0. And remember, what is this function? It's just negative x squared plus 4. When the function is 0, if I plug 0 in, I get 4. If I plug, not 1 in, if I plug 1/2 in, because that's the first line in the graph, if I plug 1/2 in, I get 3 3/4, or I get 15/4. If I plug 1 in, I get negative 1 plus 4, which is 3. If I plug in 1 1/2, if I plug in 2, if I plug in 2 1/2, and again, since I'm going to be doing so many times using these different numbers to figure out these points along my curve, I may as well just have them all written at the bottom so that I'm not calculating them every single time. So go ahead and fill in these remaining values. So here we go. If I plug in 3/2, I'm going to end up with 7/4. If I plug in 2, I'm going to end up with 0, and I don't need 2 1/2 actually, since every single one of these graphs stops at 2. So let's look up at the right-handed rectangles. Each of our rectangles has a width of 1/2. So I'm adding together 4 rectangles, each that have a width of 1/2 and a height that's being determined by the curve that we're looking at. Let's clean this up a little bit. So now, what goes in the height spot? Well, let's take a look. This height right here, this is what we get when x is 1/2, right? That's what this x value is here. And if we go down here when x is 1/2, our height is 15/4. If we look at this one, this is our height when x is equal to 1. And we know from down here, if x is 1, then the function is at 3. Similarly here, this is when x is 1 1/2 or 3/2, and we found out down here that's going to be 7/4. And the last one is what we get. We can tell this one from the graph, actually, what we get when we plug in 2, which is 0. So the area under this curve using right-handed rectangles, and notice I'm still putting approximately because this is not the exact area under the curve. This is something we're using to approximate it. We're approximating it using Riemann sums, and in this case, using right-handed rectangles. So if I find a common denominator, add all these things together, and this is where I'm telling you it's okay to use your calculator right now because this basic math is not the goal here, we end up getting that this area is approximately 17/4 units squared. Now, if we look at the left-handed rectangles, again, every single rectangle is going to have a width of 1/2, and there are 4 of them, which actually, since they all have a width of 1/2, you could actually just say 1/2 times, and then you could add the area of each of those, or sorry, the height of each of those rectangles together. It's probably a little bit easier. And I want you to see if you can fill in the height for each of those functions, then unpause the video and see how you did. So here, the height of the first rectangle is when x is equal to 0, and when x is equal to 0, the height is 4. The second rectangle is when x is 1/2. We know that when x is 1/2, we're at 15/4. The third rectangle is here. We know that that's when x is 1. When x is 1, the height is 3. And the last one here is when x is 1 1/2 or 3/2, and that's going to give us 7/4. So we could actually add all of those heights together and then multiply them by 1/2 afterwards. Regardless, if you simplify that, you get that this area is approximately 25/4 units squared. Now for the midpoint, we haven't calculated all of these function values because, again, this time I'm just going to write the 1/2 in front. The width of every single rectangle is 1/2. We have 4 heights that we need to add together. This height is halfway between 0 and 1/2, which means we need to know what f of 1/4 is. If we plug 1/4 into negative x squared plus 4 and simplify, we're going to get 3.9375, and you can just use a calculator to get that, 3.9375. And then the next height here would be at 3/4. The height here is going to be at 5/4. And the last height is going to be at 7/4. So you can go ahead and pause the video and use your calculator to find out what each of those values is. So here we go. And then if we use our calculator to simplify this, we would get that this area is approximately 5.375 units squared. The last portion here asks us to set up trapezoids instead of rectangles. So to make a trapezoid, all you're going to do is use both the left and the right-handed side to sort of make an angle there, and then draw your trapezoid. Right and left, trapezoid, right and left. Trapezoid, this last one, since it goes down to the x-axis, is actually going to be a triangle. So in case you've forgotten the area of a trapezoid, the area of a trapezoid is that you find the area, basically, that you find the area of the two rectangles that would be formed there and add them together. But what you do is you take 1/2 of the base on one side plus the base on the other side, and you multiply that by the height. In this case, since we're finding the area of 4 separate trapezoids, we're going to be multiplying 1/2 times the width, which is 2. In this case, the width is actually the height. You sort of have to think about this as if you flip it sideways. So this is our x value, which is actually now going to be the height if you think about this as a trapezoid. And then we have the 2 heights that we've been looking at. If you think about it rotated, those are going to be our 2 base values, B1 and B2. So I'm going to erase a lot of what's here so we have some more room to work through this problem. Much better. So let's look at this. I'm going to call this number 1 trapezoid. So if I find the area of this trapezoid, that's going to be 1/2 the width, which is 1/2, times what I get if I add these 2 heights together, because that would be the length of the base. Well, the first one is what I get when x is 0, and that's 4. The second one is what I get when x is 1/2, which we already said is 15/4. So that's going to be our first trapezoid. So that's our trapezoid, our first one. If we look at the second one, again, I'm going to have 1/2 times the width times, well, this first one we just said is 15/4, plus the second height here, which is going to be what? When x is 1, it's going to be 3. We're going to add that to, I'm going to call this the third trapezoid. 1/2 times 1/2 times 3 plus this height, which is what we have when we're at 3/2, which is 7/4. And we're going to add that to the last one, which is actually a triangle, but we're going to pretend we didn't notice that. So 1/2 times 1/2 times the first base is 7/4, and the second base has a height of 0, because that's what we get when we plug in 2. So we would simplify each of these expressions and add them all together, and we would get that the area is approximately 5.25 units squared. So some of this seems really tedious, but mostly the tedious stuff is the geometry. We haven't really gotten to anything crazy calculus here, other than the fact that we're approximating the area under a curve, which is something called a Riemann sum, which is a calculus topic. The last thing that I want to do in this video before we wrap up is just tie this idea, area under the curve, to a definite integral, which is sort of something that we've been talking about a little bit, run through one more example, and then we will leave the rest for the next video. So in earlier videos, we talked about an indefinite integral, and an indefinite integral is an integral that doesn't have any numbers, on the integral symbol here. There is something called a definite integral. An indefinite integral, the big difference between indefinite and definite, are these two numbers that appear on the bounds. A definite integral is defined to be the area bound between a curve and the x-axis. So now, since we're just saying bound between the curve and the x-axis, we can now include direction, meaning we can think about the area that is below as negative area, and we can think about the area that's above as positive area. So again, a definite integral is the area bounded between the curve and the x-axis. And the notation that's used for this, the definite integral over some interval from a to b, and a and b show up on those are called bounds, the bounds of integration. And that's what makes this a definite integral as opposed to an indefinite integral, which doesn't have any numbers there. A definite integral over the interval from a to b is notated in this way. So this is saying the integral from a to b of some function f of x dx. And that integral is the area under the curve. And that last part is really important. What we are talking about is the area under the curve. That is what a definite integral represents. So now, if we look at this notation, determine the integral from negative 10 to 10 of f of x dx given f of x below. So what we're being asked is to find the area from x equals negative 10 to x equals positive 10 formed in this graph below. So I want you to pause the video and draw some geometric shapes that could help you actually calculate the area under this curve using geometry. Then unpause the video and see how you did. So I'm hoping you had time to do this. I can see a triangle here. This triangle has a negative area, and if I calculate this, it has an area of 1/2 times base times height, so times 2 times 2, and since it's negative, it's going to have a negative area, so that area is going to be negative 2. So I'm going to say the integral from negative 10 to positive 10 of f of x dx equals, and I'm going to just start adding these little geometric areas together. Negative 2 plus, if I look at this triangle here, this has a positive area. This is going to be 1/2 times 2 times 8, which is going to be 8, so plus 8. If I find the area of this half of a circle here, which is going to be a negative area, negative 1/2 since it's half of a circle, of pi times r squared, and it looks like r here is 2, so of pi times 4, so this is going to be minus 2 pi. And then the last shape you could either break up into a rectangle, a square and a triangle like this, or you could consider the whole shape as a trapezoid, dealer's choice. I'm going to go the trapezoid route. So the area of this trapezoid is 1/2 times the height, which is 2, times what I get when I add the bases together, which is 2 plus 6. So that's going to give me 8. And if I add all of those areas up together, I'm going to get 16 minus 2 is 14 minus 2 pi units squared. So that's where we're going to stop in this video today. The important things I want you to remember from this video: a Riemann sum is approximating the area under a curve using geometric shapes, namely using rectangles. We talked about different types of Riemann sums: left-sided, right-sided, midpoint, inscribed, circumscribed, all of those different variations. And then lastly, we tied it to this notation, which is what most of our next video is going to focus on. How do we use this notation to approximate the area under the curve? So make sure you write down any questions you have, and I look forward to supporting you on this. Thanks for listening.